Yeah, thank you very much for inviting me and giving me the opportunity to talk. It's a great honor to talk at Paul's secret birthday conference. And I thought a long time whether I should say something funny, but I don't have anything to say. You're just a kind person, and so I will just shut up. So there are lots of things I mustn't forget. So first, I put this on the board. So this is a report on some work we did at the recent Banff Women in Topology 2 project. And these are the 5 women involved. And then there's some later part that's going back to joint work with Ayelet. And so juggling is not total bracket juggling. It's juggling with algebras and spaces. So don't have the wrong expectations. So let me put down some definitions. So the disclaimer is, maybe I should add this here on this. I will forget this. So everything is commutative and cofibrant. This is the general setup. I don't want to worry about this, so this is always in the background. So what is the setting? You take your favorite pointed finite simplicial set. And then you glue a commutative ring spectrum to it, and commutative really means strict commutative. So and then you form the tensor product of these things. And so this is the category of commutative ring spectra is enriched in finite. Well, it's enriched in simplicial sets. I want to restrict to the finite case today. You can also choose topological spaces if you like. But if you work simplicially, then this has a very nice explicit definition. So in simplicial degree n, you just take as many copies of your ring as you have simplices in your X. And then the structure maps are just induced by the structural maps in X. So this is a simplicial thing. So it has the structure of a simplicial commutative ring spectrum, and you can take realization, but you don't have to. So, and I will be vague about what I'm actually doing. You can stay in the simplicial world or go topological.
Do you really mean the smash product without any copies of A?
Yes. Okay. Well, the smash product is the co-product in the category of commutative rings. So you take the co-product of as many things as you have in your simplex. Right. So you actually all know an example of that. So if we take X to be the one sphere, and I want to take the smallest possible model, then you just have one non-degenerate 0 cell and one non-degenerate 1 cell. And if you take all the other stuff in degree n, you just get a finite set with n plus 1 points. So if you write down what that thing is, then as a simplicial object, this is just the familiar topological Hochschild complex that you're getting with all the structure maps you're used to and love. So let me take geometric realization in this example for now, but so this is just THH of A. We are interested in sort of playing with the space coordinates. So we want to vary X. So other important examples are higher dimensional spheres. This should actually get a separate name because it's sort of important. It's sort of this thing that features in the title. So as n tensor A is higher order topological Hochschild homology of A, and I denote this with this funny bracket. And a third important example is if you take n copies of a sphere So you have the N torus, and then you get torus homology. So if I write this as the N torus, then you get the N torus tensor A. And if you like K-theory, then you should like this one, because this is a target of iterated traces. Let me do the case n equals 2 just to be very explicit, then you can just write that down. So if you take algebraic K-theory of a ring spectrum, then this is again a commutative ring spectrum, so you can iterate this. So this features if you want to detect redshift by iterations of K-theory, for instance. So and then you have the trace map down to THH. So and you can apply this in two ways. You can either apply this in the inner copy and in the outer copy. And then abstract nonsense tells you, so this is S1 tensor A, tensor S1. And the enrichment in this category tells you that this is actually just the product. So here you get S1 times S1 tensor A. So you get torus homology as the target of iterated trace maps. So this is one of the motivations for studying this. And I will hopefully get back to that problem at the very end of my talk as possible applications. So if you are in this setting, there isn't much room for juggling. You only have two things, a space and an algebra. But we want space to maneuver with these things, so I'll need two more variants. The first one is, well, you don't have to work with pointed spaces, but I want to because I want to have coefficients, and I want to glue them to the base point of my space. So if I have an A module spectrum, I can glue M to the base point in my pointed space. And all the structure maps preserve that, so it will stay at the base point, and you get a theory with coefficients. That's useful. And the other variant I want to discuss is if you want to work relative to a set of ground ring. So these smashes in this construction were over the sphere spectrum, but you might choose to work over K-theory or TMF or whatever you like. Smashes over mu showed up already, so you might want to vary your base ring. So, and this just means that you replace your smash product with a smash product over R if R is your ground ring. So now you have a bit more space. But now if you try to encode this in the tensor definition, it's getting awkward. You have a ground ring, you have coefficients. So I want to have a notation that allows me to have more space for all of this. So if I do all of this together, so this is the ground ring, this is my simplicial set, I have my algebra, and I might have coefficients. If the ground ring is the sphere spectrum, I won't mention it. If the coefficients are the ring itself, I will also not mention it. So there are some sort of obvious simplifications that I will use, but this is sort of that. And that sort of should be reminiscent of what people call the Lodé construction when they study sort of higher order Hochschild homology. So that's the sort of Lodé construction. So, and now we have more space. So before I go into juggling, let me just mention a few properties that this construction has, and I want to focus, for the properties, I want to focus on the pure tensor construction. So, So some properties. A general fact is, this is coming out of the fact that this category of commutative ring spectra is tensored over pointed simplicial sets. So it has an adjoint, so it preserves push-outs. So what I want to spell out for you are two particular cases of the push-out property. And these are, if I glue things together at the base point and then tensor with A, you get a copy of X tensor A and a copy of Y tensor A. But they were glued at the base point, so you should remember this. So you put A tensor the base point, and you smash over this, but this is just A. A second instance of this push-out property is that you can formulate what a suspension is in this algebraic setting. So if you want to know what suspension X tensor A is, you can just do a homotopy push-out. And you just take X tensor A, point tensor A, which is just A and A. And then you get the suspension. So if you do this, remembering co-products are smash products, you can represent this by A smash A over X tensor A, derived smash. So that's a very useful formula that allows you to do, for instance, an inductive calculation of higher order Hochschild homology starting from THH if you want to. So that sort of simplifies things. One feature I already used here is that tensoring several times just gives you a product. That's also useful and will come up later. So here you have, let me write this here, X tensor, Y tensor A. And last but not least, you can actually tie this explicitly to the algebraic construction of Pirashvili, for instance. So if you work relative, so now I switch to Lodot notation. If you work relative to an Eilenberg-MacLane spectrum, and you insert algebraic gadgets, so K is some ground ring, commutative ground ring, A is a commutative discrete algebra, M is A module, then you just get Pirashvili's construction. So he did this in the world of algebra in this higher order Hochschild paper, but he actually did the construction for general X. So then you end up in this setting. So what is the aim of today? I want to vary the ground ring. For instance, you can try to use this for comparing the dual of the steam-node algebra to a dual of the steam-node algebra over something, or things like this. So juggling refers to the following setting. You have three algebras. Here you have the suspension. Here you have your space. So typically, you want to know something higher dimensional coming from something lower dimensional. So say you work up your CW filtration of your space or so. So you would want to know something about this. So the goal is relate the Lodot construction for the suspension of B with coefficients in C to easier things. Maybe you know more about A. Maybe A is smaller or it has some other nice features. So maybe you happen to know something about this. And then you need input how this should glue because you want to have as input the information over X. So, and this means you have also to take these things together. So, but now you get the relative versions where you work relative to A as the ground ring and relative to B as a ground ring. Just a remark, quite often these relative groups are easier to handle. You might have to do a smaller step going from A to C or from B to C than going from the sphere spectrum to C. So this might just be more manageable. So how does this work? So as a precursor, let me just mention two results from the band work, and then I'll state sort of the more general result, and then tell you about applications of that. So, what are the results? By the way, I can also work relative to R here, to some ring spectrum R, that doesn't matter. So what are the results? The first result tells you something about relating absolute Lodé constructions, so over the sphere, to Lodé constructions over R. So how can you do that? So if you have the sphere spectrum and then some intermediate commutative algebra spectrum, what you can do is you can get at the relative Lodé construction by taking the Lodé construction over of A over the sphere, but now sort of using the map from R to A to force the smash products to become smashes over R. So how do you do this? You just use the structure map. So you have a natural map from the Lodé construction here to that one. But then you pull this all together to the base point, and then you get a map to R. And this forces the smash products you had here over S to become smashes over R. So that's the first instance of a juggling formula, but that might not be that surprising. So the second instance, so this result is due to this bunch of people. Second instance is you can work your way up from THHN, so tensoring with a sphere of dimension n to tensoring with a sphere of dimension n plus 1, as follows. So you take this absolute THH group, so you tensor B over Sn plus 1, but you place C at the base point, and that's the same as sort of doing the same thing with A, but then making up for this by tensoring over THH and relative to A with C. And then adding the other relative THH group.
What maps are you assuming between like A, B, and C, or like just A and B both mapping to C?
Sorry, yeah. So here I have a sequence of commutative ring spectra, and I said everything is cofibrant, everything is commutative, so that's the setting. Yeah? So this is also to these 5 people. But the theorem I actually want to talk about is sort of taking these two things together, so not only juggling with a sphere, but juggling with some general X, and then also maybe working relative to a ground ring. So the third instance is sort of taking this together. So I have a space X, and I work relative to a ground ring. Everything is cofibrillant. Every map is a cofibration. And then I get that I want to know something about the suspension of X of B, C glued to the base point. That's the same as knowing something about the suspension of X and A, and then sort of juggling again over the relative parts like this. So, and that's due to us. So again, most applications will actually feature R to be the sphere spectrum, but I will present one application where I'm actually working over an Einberg-MacLane spectrum, so this actually gives something new even in the purely algebraic setting. So I can actually prove that for you. The proof isn't that sophisticated, so I can at least write down a sketch of a proof. Well, you just stare at a diagram, and you take different push-outs in different directions. So the diagram to consider is this one. So maybe I should give these names. So this is proof of 3. So I take this construction here that features, whose suspension features here. So if I want to get the suspension, I have to push out to C. So I do that. And then I don't do anything in the next step here, but then I actually change rings. And here I push out to C, but here I do something, and I just use the map from A to C, going from A to C by the composition of these maps to get to this construction here. And here I do the same thing. All the spaces are X's. This is why I forgot them. So here, this part of the diagram is boring. You always take the identity map, and here you multiply everything together that you can get. So what are the induced maps? So here, in both of these instances, I have to use my multiplication in C, and first I have to map A to C, and the same here. This is the same map. This is just multiplication in C. Here I use beta alpha, so this diagram commutes. And here I have the same thing, so I better take the same map. And here I just use alpha. Then here I better use beta. And then this commutes. And here I use beta and the multiplication. So, and then if you stare at this diagram, what you see is now you can take push-outs in different directions. So what happens if you take the columns first? So if you push out here again along the columns, then you always have some identity map somewhere. So the homotopy push out there is very boring. So this kills each other. You're left with that in the middle. And C and C. So if you push out once more, you get C smash C over that Lode construction. But this is nothing but deconstruction on the suspension by the push-out preserving property of that thing. So this is sort of the left-hand side of this equation, and we get the right-hand side by taking first the rows. And there you need a variant of the first theorem because you want to convert absolute Lodai constructions to relative ones. But if you do the row thing, for instance, here, what happens in this row, you replace A, you map this to C, so you smash over A. This is the effect of that push out. So if you push out in the rows first, you get the following diagram with relative Lodai constructions. So you get the suspension X R A C, and then something happens. So here you exchange the tensors over R to the ones over A, and here the same thing happens for B. So if you push out once more, you get the right-hand side of this. So you have this juggling formula. So now I want to tell you what you can do with it. You can actually do some calculations that are usually harder. So calculations with that. So I want to give you two algebraic examples, and then if I have time, I want to tell you something, how this might help to calculate torus homology. So the first is something that I found surprising, but maybe people in the audience knew that. I don't know. So I want to talk about higher order Shukla homology. So there's this paper by Shukla where he sort of defines a derived version of Hochschild homology. And there's also work by McLean on that. So Hochschild homology, if you use the naive Hochschild complex, is not a derived invariant. So if you want to repair that damage, you get Shukla homology. A fake definition is, so this is by far not the original one. So if you have a discrete commutative ring, and a map between them, then what you can do is you can form relative THH. So I define Shukla homology of K over A as just being the spectrum that I get when I plug in H of A and H of K into THH. This agrees with the old definition, and it's just a handier notion to write down. So, and I also need the higher variant of this. And so, but this is now surprise now, so you can just do higher THH of these. And hopefully understand what these invariants try to tell you about these rings. So, so let me just make some remarks. So maybe if you don't know this, so this is just derived Hochschild. So if I take homotopy groups, let me leave out the rings. And as I said, this is not the original definition. There you work with DGA resolutions, and then you get something big and ugly. And in general, this is also defined for associative rings, but I want the higher versions, and they only make sense if you plug in something commutative. So what do you know? Well, as this is derived, it should better not give something new if you're in the flat setting. But beware, A is now the ground ring, and K is the big thing. I just write this because I secretly think of this as being an augmentation map. So if K is A flat, then this is just giving you Hochschild, and you don't have to derive, and you don't produce nonsense. And just as a sample, Z mod P is not flat over Z. And if you just write down the Hochschild complex, it gives you nothing. It looks like a point. But Shukla homology actually sees that they killed a regular element. So this gives you a divided power algebra on a degree 2 generator. So this is a helpful invariant. It tells you that you killed a regular element. So what can we show with that? Yeah.
What additional structure is that equivalent to have in the case of the finite Galois extension?
This is a complicated thing. Gala extensions. So THH doesn't always have Galois descent. So we can talk about this after the talk, but there are different notion of éterness, different notion of descent, and they clash. So let's talk about this later. If you restrict to rings, everything is fine. Rings and fields, Gala extensions of commutative rings and commutative fields behave nicely, but in spectra, it's something else. So what can we prove? Shukla homology can be hard to calculate. Pirashvili's higher order Hochschild homology has several spectral sequences that you can use, so maybe that's easier. So let me write it like this. You have this setting. So if A is an augmented commutative K algebra, and if A is K projective, then so beware, this is the opposite assumption of this here. Then you can actually calculate Shukla homology from higher Hochschild homology. So you get that nth order Shukla homology of A of K over A is isomorphic to THH n plus 1, and now you work relative to the small ring. You plug in H of A, but you take it with reduced coefficients, and this is just higher order Hochschild homology of these algebras, because I assumed that I'm projective. So in particular, I wrote n greater or equal to 0. If you plug in 0, you get the old Cartan-Allenberg formula for calculating Hochschild homology via just a simple Tor group. So you recover that. Shukla 1 is Hochschild homology 2, and you can play this game. So that's sort of nice. And I will tell you later why we want these groups. We really, really want to calculate them. They show up in some other stuff. So what is the proof? Well, let's stare at this one. This is easy because I just assume projectivity, so I just have to show you that. So what does juggling give me? So what is the juggling doing? This is my ground ring. And then I'm using the unit map followed by the augmentation. So juggling for this sequence gives, so this is THH n plus 1 relative to HK, HA, HK. This is B, this is C, so I get this. And this is THH. And now you have a lot of junk that just pulls itself together. Now you restrict to A, and then you have A and C. So this is much ado about nothing. You take a lot of copies, but you tensor them over themselves, so they are just constant. This is equivalent to a constant thingy, so this is just HK. Then you get the relative THHN, HK. And now you have A and C. So this is just this, which also is much ado about nothing. You have HK and you smash about HK, so this collapses to just HK. So this is noise. What do you get at the other end? Well, you get B as the ground ring now, and HK as it is. So you can forget about these two contributions, and this is the only survivor in the juggling process, and this shows the claim. So this is nice. And some other application that, for sake of time, I will just mention is let me call this Tate examples. Is the following. What is the setting? I have a regular local ring, discrete, really algebra. And I have the maximal ideal with its residue field, and I have a regular sequence. But these elements have the extra condition that they should be in the square of the maximal ideal and not in the maximal ideal itself. So, well, it's part of this, but this is sort of this extra condition. It's in the filtration, it's from lower down. So, and then I should probably attribute this now to Tate, because if you write down juggling, what did Tate do? He calculated the relative Tor groups. So you can form R mod I, so R mod A1 up to AR, and then you can still reduce to R mod M. So, and what Tate did was to calculate the relative Tor. So, with the help of juggling, you can write down a formula for arbitrary higher order THH, but in the higher terms, the iteration is very difficult. So let me stress this is from 57. So he calculated these Tor groups. And so this is an input for us. And then you get if you want to know THH of this quotient with reduced coefficients, then what you get is something slightly easier, where you don't reduce anything. So you get THH of R with reduced coefficients that you might know because it's in your toolkit. And then, so I'm juggling with respect to this sequence. And so I'm getting, so this is now R smash R over M smash R over M over R, and here I have R over M R over M R over I. And then this is what the juggling formula gives us. So if I take coefficients, I get this Tor group. But what I can do is I get exterior generators according to the dimension of my regular ring. And then I get divided power generators for everything I try to kill. But the exterior generators also show up in the Tor of R for R mod M. So I can kill them out. So what's left is just the divided power thingies on everything I try to kill. They show up n degree 2. And here everything is over the residue field, and these things have degree 2. So what this gives you, it recovers certain calculations that are usually pretty hard. So examples is it gives you THH star of Z mod P to the M with Z mod P coefficients for M greater or equal to 2. This was due to Pirashvili and Van Buren. And we can actually get THH2 of the same thing. You just calculate, you have to calculate some Shukla homology in the next step. Well, Shukla for Z over Z mod P is easy. Shukla of Z mod P over Z mod P to the M is harder, but for M equals 2, this was done by Bauers and Pirashvili, and we just did the general case that wasn't that hard. And then you see that one thing is flat over the other, so you get an explicit tensor product formula for THH2, where all ingredients are known. So, and you get this with a full ring structure, not just additively, as you might get using Thom spectra. So that's one feature. So in the last minutes, let me just tell you something, what this might be good for. Randy complained that everybody is talking about results here, so, and not about open questions, so yeah. So I took your complaint and sort of, yeah. So what is the question? So the question raised probably first by Dundas is this Lode construction, let me just write A, is stable invariant. So what should that mean? If I have two pointed symplecture sets, and they're not equivalent, but their suspensions are equivalent, do I then get isomorphic homotopy groups on the Lode construction? So i.e., if x and y pointed simplicial sets, say finite, and I know that I have an equivalence on suspension, does this imply that, put it that way, that the homotopy groups are isomorphic? And why do you want to do this? And an immediate application would be that torus homology is easy, because if you suspend a product, it just falls apart. So an application would be, we all know that a suspension of, say, T2 is just the suspension of S1, S1, S2. So in order to calculate torus homology, you just have to calculate THH and second order THH and glue them together over your ground ring. That's nice, if this were true. So this is the question. Björn answered this himself together with Centi and showed, no, it's not true. So, and the example is embarrassingly stupid. So if you take Q adjoint T square, this is a counterexample. So you just calculate torus homology, which isn't that hard because you're with the rationals. You calculate these homology groups, and they're just not isomorphic. So now the question is, well, but we see this in certain other examples. What are the right conditions? And there's work by, oh God, now I have to get the names right. Barist, no idea how to. Ramadas, so this is Ajay, and I wouldn't even try to do that. So this is okay for Pirashvili's construction if A is a commutative Hopf algebra over a field K. Then they showed that this is isomorphic to representation homology, whatever that is, on the suspension of X plus. So you get suspension X and S1. So if you have an equivalence on the suspensions, you do get an isomorphism. So now the question is, what is the general statement? And the observation is, what might be a good question is, well, what happens if you add a circle? Maybe we don't want to have a general result, but maybe we want to understand that. So, and then juggling gives you something that sort of pins down where the obstruction for splitting is. So let me close with that. So juggling tells you that the Lode construction on X tensor A, which is nothing but this due to the iteration formula, is equivalent to the Lode construction on A with coefficients in A tensor X. And now you have an ugly tensor product. This is what it is, and this reduces to here. Now everybody of you, I mean, this is just THH of A with coefficients in something. So the natural impulse is to split this. But it has to split as a right module over that thing. And this is, so if this were split as just the Lode construction of A, and then you have an extra thing like this, then you can just stare at the ingredients. This is S1 tensor A. This is Hochschild THH if you stare at this in the right manner, because this is the enveloping algebra, and then you take an additional tensor. Everything is derived. So this is S1 tensor over A with X tensor A. And then if you write down what this is actually giving you the splitting terms. So this is a tensor X, suspension X. So the obstruction for splitting is sort of precisely that you can't do what you want to do, namely pull out these coefficients and reorder them on the right-hand side. So that actually what you get is, in certain examples, like for HFP, you stare at the according spectral sequence and you see that on the E2 term it splits, and then there's nothing more, and you can calculate it and you get a splitting on the homology groups. So this tells you, for instance, this recovers the calculation of Orsoni-Dundas for HFP, where they actually get a splitting. So at the moment, we are trying to see how far we can push that. But at the moment, we are just recovering known results and nothing new. So on this cheerful note, thank you. Well, so the original Redshift program was to prove that if you put in chromatic type N, you apply K theory, and your chromatic type N thingy is nice enough, you get chromatic type N+1 on the K theory. So in particular, if you start with something chromatic 0, a ring, and you iterate K theory twice, you should end up with something of chromatic type 2. This was shown in some examples, like the complex numbers, giving you KU, giving you K of KU, fine. But these calculations are horrible. I mean, this is not a feasible way of proving redshift. So instead, there's a program by Orsoni-Dundas who said, well, maybe we don't need the full K-theory calculation. We just do torus homology and calculate the homotopy fixed points with respect to the torus action. And then we hit this with some lower Morava connective K theory. And then they actually detect a periodicity element. But as far as I know now, they detect the periodicity element, but they don't seem to be able to show that all these powers really survive. So that's, as far as I know, the status of this. But this is why one might want to calculate torus homology, because then you can calculate the homotopy fixed points, and then you might be able to detect redshift that way, because the trace map factors over that thing anyway. So. Mark?
So, have you guys thought about trying to generalize some of this instead of the infinity to En, or become more hard, like En, kind of thing, factorization model kind of thing?
So the answer is probably yes. The problem is with En stuff, the higher you get in the dimension, the more information you lose about the multiplicative structure. So if you take an En algebra, you tensor it with Sn, then you have an n-fold delooping, so you're down to...
You're going to have this demotion of structure.
This what?
This demotion of structure.
Yes. So you just corrode everything. And the second thing is we are really playing with this enrichment in spaces or simplicial sets. So whereas in the En context, you have to put restrictions on what you do. I mean, if you want factorization homology of an En thing, your dimension is cut. So, and then juggling hits a point where you can't do anything anymore. So the thing also is that here, quite often, you can really route down the answer with the multiplicative structure. If you can't do it, then you're stuck, because you need the multiplicative structure for all these calculations, but quite often you can actually pin it down.